In my earlier video, I had seen orthogonality of vectors. I had seen orthogonality vectors have v transpose w equal to 0. And then I had seen orthogonal subspace. I had seen two subspace v and w are orthogonal when v transpose w equal to 0 obviously, but here for every vector v in the vector capital V and every vector w in the vector capital W. Next I have seen orthogonality of four subspaces. I had seen one nice picture. I had seen these four subspace as a orthogonal subspace. At first, in Rn, two subspace means row space and null space be orthogonal to each other. And this is orthogonal. Just check it again quickly because this topic is very important for any competitive exam, and not only competitive exam, also for hard study also. So I have repeated it again and again. Consider A equal to A1, A2, A3 vector and consider X belongs to null space of A. And since X belongs to null space of A, that means obviously X equal to 0 vector. Then A transpose equal to A1 transpose, A2 transpose, A3 transpose. And obviously these are the row vector. And since X belongs to null space of A, that means obviously Ax equal to 0. And Ax equal to 0 means here the matrix row 1, row 2, row 3 with x equal to 0. That means row 1 dotted with x, row 2 dotted with x, row 3 dotted with x equal to 0 vector. And since this is vector component, so I have considered row 1 as a A1 transpose, row 2 as a A2 transpose and row 3 as a A3 transpose. That means put the value. Then since this is the column vector, so column of A transpose, which is actually the row space, is linear combination of the matrix A transpose, which represent as the vector in column space of A transpose, as the vector is represent as A transpose Y. And here Y means because here the M components. Okay. Then what happens when X transpose multiply with A transpose Y? Then this would be obviously X transpose A transpose times Y. And by the property of matrix transformation, this is equal to actually Ax transpose Y. And since X belongs to null space of A, so Ax transpose obviously 0. That means this is equal to 0 transpose Y. And 0 transpose Y means equal to 0. Okay. That means X transpose with the vector A transpose Y, which is actually the row space, and this is the null space of the vector, is equal to 0 vector. That means row space are perpendicular to null space. Are you getting the idea? Well, so all combination of rows, which is actually called as row space, is perpendicular to null space. Okay. Similarly, column space is perpendicular of null space of A transpose. I had seen this in my earlier video. So there exists a nice theorem, fundamental theorem of orthogonality. The theorem states null space is orthogonal to row space of Rn and column space is orthogonal to the left null space on Rn. This theorem is fundamental theorem of orthogonality. And this theorem actually fundamental because all orthogonality depends on this theorem. Actually, all linear algebra depends on this picture, these four subspaces. So, this is very important. Are you getting? Well, in my last video, I had also discussed orthogonality complement. I had seen the orthogonal complement of a subspace V contains every vector that is perpendicular to the V, and this orthogonal subspace is denoted as V bar, which is the orthogonal complement of the subspace V. Are you getting? I had discussed this topic in my earlier video. So by definition, I had seen the null space is orthogonal complement of row space. And this is orthogonal complement because the null space is orthogonal to each row vector. So the null space is orthogonal complement of row space. Okay. Now I will see the fundamental theorem of linear algebra. The theorem is, since null space is the orthogonal complement of the row space in Rn and null space of A transpose is orthogonal complement of column space in Rn, and if dimension of row space equal to R, we all of us know the rank of A. This is actually dimension of row space, that means linear independent column in the matrix A, and also rank of A equal to rank of A transpose. Therefore, since dimension of row space equal to R, then dimension of null space would be n minus R. That means, since null space is orthogonal to row space, so every vector x can be split into component of row space and component of null space. Are you getting? That means every vector x is written as component of row space and component of null space. Now multiply this equation with A. Then this would be x equal to axr plus axn. And the null space component goes to axn equal to 0. Then the row space component goes to the column space axr equal to x, which is actually equal to b. So every vector b in the column space come from one and only one vector xr in the row space actually. And see the picture. Here the element xr, and when I will apply A, then I will get B in the column space. And notice here the solution of null space. When I will apply A, then this would be just 0 vector in the space Rm. Okay, are you getting the picture? I hope my all viewers have understood now clearly this picture. This picture is very important for all linear algebra. Actually, all linear algebra constructed on this picture. Now just recall this solution x equal to b solution for which condition there exists a unique solution. Uniqueness always implies, we all of us know, existence, and existence implies uniqueness. That implies actually when A is invertible. Actually, when there exists no pivot in the matrix A, we all of us know, then the solution is unique solution. Also, in different way, opposite way, existence implies uniqueness. The opposite direction is such type Suppose x equal to b can be solved for every b. That means this is the picture. X equal to b here solved for every b. That means actually there exists no zero rows in the matrix A. That means there are n pivots and no free variable. That means null space contain only zero vector. That means here the matrix in the matrix A there is no pivot. That means only zero vector be the null space and whole Rm be the column space. Are you getting the picture? Well, then the solution is unique solution. We all of us know this is. For this picture I have repeated this also. I had defined this topic elaborately in my previous video. Means actually the fundamental theorem on linear algebra is, let A be an m cross n matrix in the field f of m cross n, then every vector v in fn can be written as uniquely as a sum of vectors such that v equal to v row of A plus v null of A. When v row of A belongs to row space of A and v null of A belongs to null space of A. In particular, the orthogonal complement of row space of A is null space of A. Furthermore, if AV equal to B be a solution, then V row space of A is actually the particular solution of Ax equal to B, and V null space of A is the associate solution of the homogeneous equation Ax equal to 0. We all of us know this part is very useful for differential equation to find the particular solution and associated solution of x equal to 0. We all of us know this is. And likewise, every vector w in Fm can be decomposed uniquely as a sum of vectors, which is actually any vector w can be written as w column space of A plus w null space of A transpose, where w column space of A belongs to whole column space of A and w null space of A transpose belongs to null space of A transpose. And obviously we all of us know the orthogonal complement of column space of A actually the null space of A transpose. Furthermore, if A transpose W equal to B, then W column space of A, similar to before, here this is the particular solution of the linear system of equation. Here notice the linear system of equation here A transpose Y equal to B, and W null space of A transpose is the solution of A transpose Y equal to 0. Here the solution is A transpose Y equal to B, and here the solution of A transpose Y equal to 0. Now look the picture. I hope my all viewers have understood very clearly now this picture. Okay? Well, so all concept leads a nice theorem, rank nullity theorem. The statement of rank nullity theorem is, for a linear transformation T from U to V, which corresponds a m cross n matrix such that rank T plus nullity T equal to dimension of V, or rank of A plus nullity of A equal to dimension of V. The mapping is such type. Here the transformation T from U to V. This is the transformation U to V, and this corresponds a matrix m cross n. That means the mapping from Rm to Rn. Okay. Now I will give one idea about the matrix A transpose A. I will discuss about this matrix because this topic is very important for any competitive exam about this matrix. We all of us know the non-homogeneous equation Ax equal to B is unsolvable if m greater than n. That means if number of equation greater than number of unknowns, then this solution is unsolvable. We all of us know this is. Now multiply both sides by A transpose. Then A transpose A is a square and symmetric matrix. And A transpose A is not invertible always. And in fact, null space of A transpose A always equal to null space of A. And rank of A transpose A equal to rank of A. And A transpose A is invertible when null space contain only the zero vector. That means when A has a independent column, then obviously the A transpose A is invertible. This type of idea is very important for any competitive exam. Are you getting? Oh. Now let's come back our original discussion. I will see basis of orthogonal complement. The example is, consider W be subspace of R4 where W contain the set alpha beta, alpha plus beta, alpha minus beta, where alpha beta belongs to R. Then what is the W part? Notice at first the basis of W as, consider the vector E1. Notice here, notice the set. This is 1 0 1 1. Then U2 equal to 0 1 1 minus 1. Then any vector in W is of the form alpha u plus beta v, where alpha beta belongs to R. That means obviously these two vectors are basis of W, because W is generated by these two vectors, which are linearly independent. Now I will see basis of W part. What is the basis of W part and what is the actual? At first we have to find what is W part. Consider X belongs to W part. Suppose X is orthogonal to U1 and U2. That means by definition, inner product X with U1 equal to 0 and inner product X with U2 equal to 0. And if we multiply any scalar alpha and beta, then this would be inner product X with alpha U1 equal to 0 and inner product X with beta U2 equal to 0. And add them, these two. Then this would be inner product X with alpha U1 plus beta U2 equal to 0. And that implies, since U1 and U2 be the basis of W and any vector of W is of the form alpha u plus beta v, that implies X is orthogonal to every vector of W. Are you getting? Because every vector of W is written as alpha u plus beta v. Since X is orthogonal to every vector of W, that implies X obviously belongs to W part. Okay? That means here the vector is such type of W part. Since X is orthogonal to U1 and U2, that means inner product X with U1 and inner product X with U2 equal to 0, then that implies, obviously, notice since U1 equal to this vector and U2 equal to this vector, then that implies x1 plus x3 plus x4 equal to 0 and x2 plus x3 minus x4 equal to 0. That implies x1 equal to minus x3 minus x4 and x2 equal to minus x3 plus x4. Therefore, W bar contain the vector such type minus alpha minus beta minus alpha plus beta alpha beta, where alpha beta belongs to R. Are you getting the vector of W bar? Well, that means basis vector of W bar would be -1, 1, 0 and -1, 1, 0, 1. Okay? Have you understood how we have to find any basis vector of W bar? What is the orthogonal basis? An orthogonal basis is a basis for a vector space V that is actually orthogonal set. As for example, if we consider in R3 this standard basis, notice here each vector be orthogonal because inner product be 0. So, this basis is orthogonal basis in R3. Are you getting what is the orthogonal basis in the vector space? Well, here one new extra condition be added in basis, orthonormal basis. Orthonormal basis is those set in which norm be equal to 1 for all V belongs to capital V. Are you getting? Well, notice this basis. This basis not only not orthogonal, this is also orthonormal basis because here norm be equal to 1. Now let's see some example of orthonormal basis. Standard basis in Rn or Cn. Obviously this is orthonormal basis. Similarly standard basis of M cross N matrix. But if we choose the standard basis of polynomial on the closed interval AB, then notice inner product 1 with x square not equal to 0. That means actually these bases are not mutually orthogonal. That means all standard bases does not always imply they are mutually orthogonal. Are you getting what is orthogonal basis and what is the orthonormal basis? Well, today I will stop here. In my next video, I will discuss this topic also elaborately because this topic is very important for any competitive exam and also for higher study. So, please pay attention in this topic. And if you have any queries about this topic, please do comments in comments box. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.